Metermain can be used instead of a meterbase. The main difference between the two is their location. A meterbase is typically mounted to the outside of a building, whereas a metermain is installed inside. When grounding a service, you can add a number 4 copper ground wire to the conduit and separate the neutral and ground buses within the panel. This is acceptable under specific conditions. Firstly, the conduit must be either rigid metal conduit or intermediate metal conduit, often referred to as IMC. Secondly, the conduit needs to be bonded to the ground rod at the service entrance. Thirdly, ensure that the neutral and ground buses inside the panel are completely isolated from each other. Regarding SER cable, a 4-wire 200 amp service entrance cable commonly uses 4/0, 4/0, 4/0, and 2/0 aluminum conductors. The additional 4/0 conductor in this configuration is specifically designated for grounding purposes. When it comes to bonding gas and water pipes, the bonding connection does not have to be located within 5 feet of where the pipes enter the building. However, it is best practice to make the bonding connection as close as practically possible to the service entrance. Let's delve deeper into each of these aspects, starting with metermains and meterbases. A meterbase, being typically outside, is more exposed to environmental elements such as weather and potential physical damage. This necessitates a robust enclosure and installation practices to ensure its longevity and safety. Metermains, on the other hand, being inside, are relatively shielded from these factors, potentially simplifying their installation and maintenance. Moving on to grounding, the selection of a number 4 copper ground wire is based on the size of the service conductors as dictated by the National Electrical Code, or NEC. The NEC Table 250.102 current dictates the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. This ensures that the grounding conductor is adequately sized to handle any fault current. The type of conduit used is also crucial. Rigid metal conduit and intermediate metal conduit provide a continuous, low-impedance path back to the source, which is essential for clearing ground faults quickly and safely. This is why the NEC requires that the conduit itself be bonded to the grounding system. Bonding the conduit to the ground rod at the service entrance ensures that any fault current flowing through the conduit has a direct path to ground. This is typically achieved by using grounding bushings and bonding jumpers. It's also critical to maintain the isolation between the neutral and ground buses within the service panel. This separation prevents neutral current from flowing through the grounding system, which can lead to unwanted voltage on metal parts and create a shock hazard. The neutral bus is connected to the neutral service conductor and is typically insulated from the panel enclosure. The ground bus, on the other hand, is bonded to the panel enclosure and connected to the grounding electrode system. The 4-wire SER cable configuration, with its additional 4/0 conductor for grounding, provides a dedicated grounding path. This is particularly important in services where the grounding path through the conduit may not be sufficient. The dedicated grounding conductor ensures a reliable and low-impedance grounding path. Finally, the bonding of gas and water pipes is essential for creating an equipotential plane within the building. This means that all metal parts are approximately the same electrical potential, reducing the risk of electric shock. While the NEC does not specify a maximum distance from the service entrance for bonding these pipes, it recommends doing so as close as practical. This is because the further the bonding connection is from the service entrance, the greater the potential difference between the pipes and other grounded metal parts in the building. It's important to use appropriate bonding clamps and conductors that are sized according to the NEC to ensure a reliable connection. Now, let's discuss each of these points in more detail to provide a more complete understanding. Focusing first on the selection between a meterbase and a metermain, several factors come into play. These considerations extend beyond just the location of the equipment and include accessibility, environmental factors, and local utility requirements. When a meterbase is chosen for an exterior installation, it is vital to select a unit rated for outdoor use. This rating, often indicated by a NEMA enclosure type such as 3R or 4, ensures that the enclosure is resistant to rain, snow, and ice. Furthermore, the meterbase should be mounted at an accessible height for meter reading and maintenance by utility personnel. The mounting location should also be free from obstructions and readily visible. In contrast, a Metermain installed indoors benefits from the protection of the building envelope. This reduces the exposure to weather-related deterioration and physical damage. However, indoor installations must still comply with accessibility requirements, ensuring that the Metermain can be safely accessed for maintenance and repairs. It is also crucial to consider the available space and the layout of the electrical room when planning an indoor installation. The utility company often has specific requirements for the placement and clearance around the Metermain, and these must be carefully followed. Moving to grounding considerations, the use of a number 4 copper grounding electrode conductor is predicated on the size of the service entrance conductors. According to NEC Table 250.66, a 4/0 aluminum service entrance conductor requires a minimum number 4 copper grounding electrode conductor when connected to ground rod or ground plate electrode. This requirement is designed to ensure that the grounding electrode conductor can safely carry the maximum fault current that may occur under service. The choice of rigid metal conduit, or RMC, and intermediate metal conduit, or IMC, as acceptable raceways for service entrance conductors is based on their mechanical strength and grounding capabilities. Both RMC and IMC provide a robust, continuous metallic pathway that can serve as an equipment grounding conductor. This means that in addition to the grounding electrode conductor, the conduit itself can help carry fault current back to the source, enhancing the safety of the electrical system. However, to ensure that the conduit functions effectively as a grounding conductor, it must be properly bonded at all connections and terminations. This is typically achieved using threaded couplings and connectors that are tightened securely to create a metal-to-metal contact. The requirement to bond the conduit to the ground rod at the service entrance is a critical safety measure. This bond ensures that the entire conduit system is electrically connected to the grounding electrode system, providing a low impedance path for fault current. The bonding connection is typically made using a grounding bushing and a bonding jumper. The grounding bushing is installed on the end of the conduit, and the bonding jumper connects the bushing to the grounding electrode conductor or the ground bus in the service panel. Maintaining the separation of the neutral and ground buses in the service panel is essential for preventing objectionable neutral current. In a properly wired system, the neutral conductor carries only unbalanced current from the branch circuits. The grounding conductor, on the other hand, should only carry fault current. If the neutral and ground buses are connected, neutral current can flow through the grounding system, creating a potential difference between grounded metal parts and the earth. This can lead to electric shock hazards and can also interfere with the operation of sensitive electronic equipment. Therefore, it is crucial to ensure that the neutral bus is insulated from the panel enclosure and that the grounding bus is bonded directly to the enclosure and the grounding electrode system. Shifting our focus to service entrance cable, or SER cable, the use of a 4-wire configuration with an additional 4/0 aluminum conductor for grounding provides a dedicated grounding path that is separate from the neutral conductor. This is particularly advantageous in services where the conduit system may not provide an adequate grounding path. The dedicated grounding conductor ensures that fault current has a lower impedance path back to the source, minimizing the voltage rise on grounded metal parts and reducing the risk of electric shock. The size of the grounding conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.102 colon. Finally, regarding the bonding of gas and water pipes, the primary purpose of this requirement is to create an equipotential plane within the building. By bonding all metal piping systems together into the grounding electrode system, the potential difference between these systems is minimized. This reduces the risk of electric shock if a person comes into contact with two different metal parts that are at different potentials. While the NEC does not specify a maximum distance from the service entrance for bonding these pipes, it is generally recommended to make the bonding connection as close as practical. This minimizes the impedance of the bonding conductor and ensures that the piping systems are effectively bonded together. The bonding conductor should be sized according to NEC Table 250.102 colon and should be securely connected to the piping system using approved bonding clamps. It is also important to ensure that the bonding connection is accessible for inspection and maintenance. By adhering to these guidelines and requirements, electricians can ensure that electrical systems are installed safely and in compliance with the NEC. This protects people and property from the hazards of electricity and helps to ensure the reliable operation of electrical equipment. To add another layer of understanding, let's consider some practical examples of how these concepts are applied in real-world situations. Imagine a scenario where a new 200 amp service is being installed in a commercial building. The electrician has chosen to use a Metermain instead of a Meterbase due to aesthetic considerations and the availability of space inside the building. The Metermain is mounted on an interior wall in a dedicated electrical room, providing easy access for maintenance and meter reading. The service entrance conductors are run in rigid metal conduit from the meter to the Metermain. The electrician carefully bonds the conduit to the ground rod at the service entrance using a grounding bushing and a bonding jumper. Inside the Metermain, the neutral and ground buses are kept separate. The neutral bus is insulated from the enclosure, while the ground bus is bonded directly to the enclosure and connected to the grounding electrode system. The electrician uses a number 4 copper grounding electrode conductor to connect the ground bus to the ground rod, ensuring that the grounding system is properly sized and installed. In another scenario, consider a residential installation where the electrician is using SCR cable for the service entrance conductors. The electrician chooses a 4-wire SCR cable with an additional 4/0 aluminum conductor for grounding. This provides a dedicated grounding path that is separate from the neutral conductor. The electrician connects the grounding conductor to the ground bus in the service panel, ensuring that it is securely fastened and properly sized. In both of these scenarios, the electrician pays close attention to the details of grounding and bonding, ensuring that the electrical system is installed safely and in compliance with the NEC. By following these guidelines, the electrician can protect people and property from the hazards of electricity and help to ensure the reliable operation of electrical equipment. Furthermore, it is important to stay up to date with the latest changes and interpretations of the NEC. The NEC is revised every 3 years, and each edition may contain significant changes that affect the way electrical systems are installed. Electricians should attend continuing education courses and read industry publications to stay informed about these changes. It is also important to consult with local electrical inspectors to ensure that installations comply with local codes and regulations. Electrical inspectors are responsible for enforcing the NEC and other applicable codes, and they can provide valuable guidance and feedback on electrical installations. By working closely with electrical inspectors, electricians can help to ensure that their installations are safe and compliant. Additionally, always refer to the specific requirements and regulations of the local utility company. Utility companies often have their own standards and specifications for electrical services, and these may differ from the NEC in some respects. It is important to be familiar with these requirements and to ensure that installations comply with them. Utility companies may also have specific requirements for the type of metering equipment that is used and the location of the service entrance. By following the utility company's requirements, electricians can help to ensure that the service is properly connected to the grid and that the metering equipment is functioning correctly. In summary, understanding the differences between metermains and meterbases, proper grounding techniques, SCR cable configurations, and gas and water pipe bonding locations is essential for electricians. By following the guidelines and requirements of the NEC local codes and utility companies, electricians can ensure that electrical systems are installed safely and in compliance with all applicable regulations. This protects people and property from the hazards of electricity and helps to ensure the reliable operation of electrical equipment.